NASA loses one file, and a piece of the universe is gone forever. Every single day, NASA's ground stations receive 1.73 terabytes of raw data from space. That's enough to fill roughly 350,000 songs every single day, streaming in from probes, telescopes, and rovers scattered across the solar system. But here's what makes this unlike any other data problem on Earth. This data is irreplaceable. You cannot retake a photograph of a supernova that happened 4 billion light-years away. You cannot ask Voyager 1 to fly past Jupiter again. Every byte lost is a scientific observation that simply ceases to exist. NASA's total archive today holds over 100 petabytes of scientific data. To put that in perspective, 100 petabytes is roughly equal to 22 times the text content of the entire internet as of the year 2000. And that number grows every single day. So how does the data even get to Earth in the first place? It all starts with the Deep Space Network, a system of enormous radio antenna dishes positioned at 3 sites around the globe. One in Goldstone, California, one in Madrid, Spain, and one near Canberra, Australia. These are not ordinary satellite dishes. The largest antennas in the Deep Space Network measure 70 meters across, nearly as wide as a 23-story building is tall. They are some of the most precise mechanical instruments ever built by humans. The signal arriving at these dishes is almost incomprehensibly faint. Voyager 1's transmitter puts out just 22 watts of power, about the same as a refrigerator light bulb. By the time that signal crosses more than 24 billion kilometers to reach Earth, it is 20 billion times weaker than the power needed to run a digital watch. Once captured, the raw signal is decoded and processed at the Jet Propulsion Laboratory in Pasadena, California. JPL acts as mission control and the first data gateway. From there, validated data packets are forwarded to the appropriate science archives across the country. NASA doesn't have just one archive. It operates a distributed system of specialized data centers called the NASA Science Mission Directorate Archives. Each one is dedicated to a specific science domain: astrophysics, planetary science, Earth observation, heliophysics, and more. Let's zoom in on the Earth Observing System Data and Information System, OSDIS. This single archive handles the biggest data volume of all NASA science. It manages over 50 petabytes of Earth imagery and climate data across 12 specialized distribution centers called DACs, spread from Alaska to New Hampshire. Now for the most critical question. How do you make sure none of this data ever disappears? NASA follows a strategy built on 3 layers of protection. First, redundant on-site copies. Second, geographically separated backups. And third, format migration, actively converting old formats before they become unreadable. The physical storage itself is a layered hierarchy. The most frequently accessed data lives on fast solid-state drives and spinning hard disks, called hot storage. Data needed less often moves to warm storage, tape libraries, and lower-speed drives. And the deepest archives go into cold storage, massive robotic tape silos that can hold petabytes at a fraction of the energy cost. Tape might sound old-fashioned, but it is still the gold standard for long-term archival storage. A single modern tape cartridge can hold up to 30 terabytes of data. It requires no power when idle. It has a rated shelf life of 30 years, and the cost per terabyte is roughly 1/20th the cost of hard disk storage. One of NASA's most impressive cold storage facilities is at the Goddard Space Flight Center in Greenbelt, Maryland. Here, a robotic tape library called the GSFCA Mass Storage System houses tens of millions of tape cartridges. Robotic arms move silently through the racks, retrieving specific tapes on demand with millimeter precision. But physical redundancy is only part of the equation. NASA also guards against something called bit rot, the gradual, silent corruption of data as magnetic charges decay over time. To fight this, every archived file is assigned a cryptographic checksum, a unique digital fingerprint. Automated systems re-verify every checksum on a regular schedule, catching corruption before it spreads. Geographic redundancy is equally important. NASA's key data archives are mirrored across multiple physical locations, often hundreds or thousands of kilometers apart. This protects against earthquakes, floods, fires, and even power grid failures. If one data center goes dark, another has the full archive ready to serve. NASA also relies on the international community. Through partnerships with the European Space Agency, JAXA in Japan, and other national agencies, some mission data is mirrored on overseas servers. This creates a truly planetary safety net. No single nation's infrastructure failure can erase a mission's legacy. Format obsolescence is a surprisingly underrated threat. Early NASA missions recorded data on 9-track magnetic tapes in formats that modern computers cannot read. NASA has actually lost access to some data from the 1960s and 70s, not because the tape degraded, but because the machines to read them no longer exist. This is why active format migration programs are now mandatory. The James Webb Space Telescope has introduced a new era in data volume. In its first full year of operations, Webb generated roughly 61 terabytes of science data, more than 8 times the amount NASA's older Hubble telescope generates in an equivalent period. Each Webb image can be up to 150 megabytes, a single raw image larger than many people's entire photo libraries. Cloud computing has entered NASA's arsenal too. In recent years, NASA has partnered with commercial cloud providers to offer public access to petabytes of open data. Programs like NASA Earth Data on Amazon Web Services let any researcher in the world query and process massive datasets directly in the cloud, without downloading a single file. What about the data still traveling toward us right now? Voyager 1, launched in 1977, is still transmitting. Its signal takes more than 22 hours to reach Earth at the speed of light. The spacecraft sends data at a trickle, just 160 bits per second, slower than the earliest commercial modems. Yet every single bit is precious. The data coming from Voyager isn't just interesting, it's scientifically unique. Voyager 1 crossed into interstellar space in 2013, becoming the only human-made object ever to do so. The plasma, magnetic field, and particle data it collects exist nowhere else in any archive on Earth, because no other instrument has ever been there. The data growth rate is accelerating. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will generate roughly 500 terabytes of data per year, nearly 1,000 times what Hubble produces annually. NASA is already engineering the storage infrastructure to handle it before the telescope even launches. To manage this exponential growth, NASA is investing in artificial intelligence tools to help with data triage and compression. Machine learning models can identify scientifically valuable observations and flag them for priority preservation. They can also detect anomalies in downlink data, catching transmission errors that human reviewers might miss. The Open Archival Information System, or OAIS, is the international standard framework that NASA and most major space agencies use to structure their archives. It defines how data is ingested, described, stored, and eventually made accessible to the public across decades. Think of it as the universal rulebook for preserving knowledge across generations. There's one more dimension to this story that often goes unnoticed: energy. Keeping 100 petabytes of data alive, in temperature-controlled server rooms, spinning drives, and robotic tape systems running around the clock, consumes enormous amounts of electricity. NASA's data centers are increasingly powered by renewable energy to reduce this footprint. Let's step back and look at the full picture of what we've covered, from the moment a photon leaves a distant star to the moment a scientist opens a data file on their laptop. The journey crosses billions of kilometers of vacuum, 22 watts of radio power, 70-meter dishes, fiber optic cables, petabyte tape libraries, and cryptographic checksums, all working together every single day. What we're really talking about is not just data management. It is the preservation of humanity's memory of the universe. Every image of a dying star, every reading from the edge of the solar system, every measurement of a distant world, archived and kept alive so that scientists 100 years from now can make discoveries we cannot even imagine today. 1.73 terabytes per day, 100 petabytes preserved, 3 copies minimum spread across continents and oceans, tape libraries, cryptographic checksums, cloud mirrors, and international partnerships, all standing between the universe's secrets and oblivion. The next time you see a NASA image, remember, keeping that image alive is itself a feat of engineering as remarkable as capturing it.